Alright, time for the draftphysics.com, debatephysics.com also, but nobody debates. Alright, so there are comments now and then. So one comment says, there's just so few on the regular YouTube videos. Hey DraftScience, have you ever watched the Kurt Jamal videos about theories of everything? So yes, I have. I've pointed out how none of those people are doing anything called physics, and they're not theories of everything. The whole channel's a big lie. And frankly, after he did that silly contest where the wooiest, silliest things got, won, it's just obvious the guy's a nut. He talks to UFO people. I mean, come on, get real. He might as well just do flat Earth videos. Fuck you. Anyway, I think you could be a very good guest to explain your theories there. Yes, I've suggested that, frankly, if he's going to do theories of everything, he should give me the opportunity to explain to him how it really works. But he wouldn't give me that opportunity. He kept griping that I was nagging him and all this other crap. And he's has a busy life and he can't get to anything and he can't do anything. And I said, well, look at the 5-minute video. Watch a 5-minute video. And if you can't answer, if you don't have an answer to the 5-minute video, then maybe you should let me talk about it. Anyway, couldn't get anywhere with him. He's obviously got his own agenda, and his agenda is woo physics. Nonsense, baby talk, rubbish shit. Okay? He's just another shit talker on the internet. Frankly. Period. End of that story, I guess. Alright, so the Leska guy had made some comment on one of the stupid clay videos somewhere. And I just thought it was worthy of the counter description of reality. So I have pointed out lots of times that you can make something way more, okay, that is, be more trouble to move by moving it slower. So the slower you lift something in gravity, the more work you will do. And of course NASA knows this. I mean, they don't lift rockets off really slow and just kind of fly into the atmosphere and just take their time. No, the idea is to, expend as much energy in the beginning as possible so you can get the most velocity possible to get through the gravity as quickly as possible. Because the quicker you get through it, the less of it you'll actually have to fight. So it's all about time. I mean, it's just so frickin' true. And it's amazing that I have to make physics videos explaining that simple idea, that the faster you get through the rain of gravity, all right, the less rain, okay, you'll have to deal with, the less work you'll have to do. The faster you can get into, the further you can get from the gravitational source, that is, the weaker and weaker the gravity gets, the further and further out you go, the less work you'll have to do. And the more you just linger around in the gravity, taking your time, the more work you'll have to do. I mean, this is just so, this isn't even something, this shouldn't be close to a debatable subject, and yet I have to debate it. It's just so bad. So you could have an experiment, it's a little different. I'm thinking maybe this one's worth doing, where you're just going to smash a little peg, round peg and square hole, doesn't really matter, but you're going to pound something into the ground, let's just say. And you could say, well, I could, hit it 4 times, okay, with a weight. I could put a weight on it, push it down. Put a weight on it, push it down. Put a weight on it, push it down. So I could take 1 pound, and I could put 1 pound on top of it, and then let it fall. And I could put another pound on top of it and let it fall. And I could put another pound on top of it and let it fall. And that would essentially be 4 units of time. Okay, I'd have to use 4 units of lift and fall. So I get 9.8 per each one, because that's how gravity works, right? 9.8 per each one, 9.8 per each one. And the counter argument is if I drop it from 4 times the distance, would it knock the peg just as far? So if I dropped it from that height, so I did this one height 4 times versus doing the 4 heights in just, so this is 2 seconds, so that's what we know, right? This is only 2 seconds in the gravity. This would be 4 seconds in the gravity. All right, and so the truth is that if I did it this slow way, lift it up, drop it, 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 I'm going to get 4 units of time worth of gravity. Gravity will have 4 units of time to work on this, where if I do it this way, it's only 2 units of time. I only collected 2 units of energy from the gravity. So it's a good experiment in the sense that, yes, doing it in 4 units of time will push it further than if I do it this way, because this is only 2 units of gravity collected. So hitting it with the 16, the twice the velocity, hitting it with twice the velocity, okay, will not be the same as hitting it with 1 velocity 4 times. Okay. No, hitting it with 1 velocity 4 times will be twice the work, and you'll do twice the work on the thing you're trying to push into the ground. So it might be a good experiment just to, again, prove this point. So again, the point is that you're sitting there saying, look, okay, I mean, the Leibnizian theory that the 4 pounds, okay, dropped 1 foot is the same, okay, as 1 pound. Okay, it's not even 2 pounds, it's just 1 pound. I should have just used the eraser. 1 pound dropped 4 feet. Okay, so I mean, I mean, we can, you should be able to logically say, come on, how could that possibly be true? You people won't even accept that the 2 is the same. You're saying the 2 is twice as much? Come on. Well, anyway, so I mean, what's the theory? It's going to be 1 pound in the gravity for 2 seconds, or 4 pounds for 1 second. Obviously, the 4 pounds for 1 second's got to be more. Okay, force. It collected more force. It now has more weight when it hits the surface. I mean, come on. This isn't brain surgery. Yeah, all right. So but the illustration is the fact that the falling velocity is the key to it. If I lift this up, if it falls in 2 seconds, right? This takes 1 second, this distance. So this is 1 second for this distance. And we know this is 2 seconds for 4 times the distance. So you know that if you're going to lift it, and you're going to lift this at the same rate, that you have to lift this going twice the velocity. And if you lift it slower than that, then you're going to do more work because you're going to be in the gravity more time. So obviously you can make this a lot more work than this. But the truth is if you lift it at the right speed, this will be a lot twice as easy to lift as this will be. The 1 pound 4 feet is, again, you're only fighting 2 seconds of gravity, where you're fighting 2 seconds at only 1 pound. So I mean, it's it's 1/4 the weight. And this is 1 pound, 4 pounds at a full second. So it's obviously going to add up to more work. All right. So going from there, I guess we'll do a little bit. I did watch, the Brozo has made a video. It's just so bad. Again, trying to defend this notion that somehow it's not about how long you're in the gravity, somehow it's about how far you travel in the gravity or something. I don't even know what they think, because I think I've already provided pretty clear evidence that it can't be true. I mean, the whole idea of something coming into gravity with a velocity already, it already has a velocity, and it's clear that it's not about the distance anymore, it's just about the time. And the faster I go through gravity, the less I'm going to add to my velocity. And the slower I go through the gravity, the more it's going to add to my velocity. I mean, undeniable facts. Alright, so the Brozo has done a Ian Gosling style experiment where he's dropping a weight, okay, on a clump of clay this time instead of Play-Doh, and claiming that he's going to prove, okay, that the half mass has twice the energy. Okay, so the half mass from 4 times the distance has twice the energy of the full mass, the 2 mass from 1 unit of distance. twice the velocity equals, this is their argument, 4 times the energy. Now, I don't know why they just don't do that experiment, but whatever. Easy enough to do that one too, and prove that point. But anyway, yeah, 4 times the energy. 4 times the distance, 4 times the energy, which isn't true. Okay, so anyway, so he does this. It's doing the experiment, right, with this big giant cube of clay, right? So let's say the cube of clay is this size. He's doing the experiment based on this much difference, right? The one object crushes the clay this much, and the other object crushes the clay this much. So it's like doing a spring experiment, where you only use a tiny fraction of the spring. It doesn't make any sense. I mean, you want to be able to see the difference. You want to make it visual. So you'd use like 1/4 of the amount of clay he's using, or even 1/8. I mean, he's using 90% more clay than is necessary to do the experiment. So it's obvious, in my opinion, pretty obvious, that you're not going to get a very good measurement, because yes, you're displacing clay in directions that you're really not going to get a very good measurement of in terms of the total mass that you're pushing. This whole giant surface, for example, it's completely unnecessary. So yeah, it'd be much better to measure, with a smaller amount of clay, where the differences would look like this. The differences would be dramatic, in terms of a visually easy to detect, visually easy to see. And so it's just, so why? You say why? Why is he dropping the weight on a gigantic clump of clay? Why is he doing it? Why? Because it's the only way he can make the results come out his way. That's why. Of course. There's no reason. It's just too silly. So I mean, it's just filmed in, shit-o-vision, and the whole thing is terrible. No quick releases. Again, this isn't that complicated, to kind of understand that this is a really subtle difference. All of the difference between the, dropping it 4 times the height versus dropping it 1 unit of height. All the difference just happens, once you've established that quicker velocity. I mean, they start off exactly the same, and it's only like 1 unit of velocity difference in terms of this quadratic function. So, you go from weighing 120 pounds to weighing 240 pounds, with just a subtle change in your velocity. Once you've accrued the velocity, the numbers go up and up dramatically. And so any subtle difference you make in terms of, well, you didn't drop this one from quite, it's a centimeter short, that centimeter is going to make a difference in the total, because it's getting bigger, and the amount of energy, the amount of velocity is increasing kind of quadratically with the distance. So I mean, it's just, you're denying the amount of time. You're changing how much time it's really in the gravity, and therefore how much time it really has to collect energy. So you really do have to, a quick release is just, it's so little work to be able to just, suspend the object by a string and cut the string. It's not that big a deal. And you can see Brozo's in the dark searching for the right line. He can't, he can't see it. It's so bad in terms of, any kind of notion of being at all precise. And again, a subtle difference does make a big difference in what you're going to get as a result. So, they just couldn't care less about doing the experiments carefully enough to be taken seriously. And they always figure out some gimmick, some way to make it so, I do have good reason to doubt. All right, let's see if there's anything else to say. I could just go through all the arguments I've already gone through, but I mean, this idea that gravity is something you collect based on the amount of time you're exposed to it, that it is like photons, it's a sunburn. It's not about how much movement you do in the sun, it's about how long the sun's hitting you. I just can't believe I have to argue that argument. I mean, it's just so obvious. The facts are so dramatically in favor of realizing that that's how it works. And to have to re-argue it and re-argue it. Again, I've already made these arguments, so go look at the videos for the last week and you'll see all those arguments in there, because there's no point in making them over and over again, and no one's countered them with anything. I mean, zero counter argument. So the Leska guy basically says that, yes, if I lift it, if we're taking 4 seconds, if I use 4 seconds of gravitational energy, I'll end up with the same amount of impact as the 4 pounds. But that's because I took 4 seconds. I used 4 seconds of gravity on a 1 pound. So yes, if I apply gravity for 4 seconds to 1 pound, I can make 1 pound equal 4 pounds. But only then. If I do it the way gravity works, which is it only takes 2 seconds to go 4 units of distance, I'm only going to get 2 units of gravity, and I'm only going to have 2 units of force. And those are just solid facts. Alright, so similar subject, but anyway, this is such a good experiment. It's just really neat. I found, so this is Pete Von Weirder. I think that's what it says. Anyway, and it's this cart crap, okay, launching 2 carts. And what it really demonstrates is that the spring pushing the carts is basically saying I'm going to give the same energy to both sides. And it gives it in the form of velocity based on weight. And the fact is that it obeys, no matter what size carts I use, it will obey the law of the lever, in the sense that I'll get the right velocity to create the right distance to balance the lever. So if it was a cart, you know, he's not doing carts that have a 2-to-1 relationship, so it's a 1 to 1.5, whatever it is. You know, 750 versus 1250. So instead of 1500, it's 1250, and it still works. But the point is, it would work even better if it was 750 and 1500. The point is that it'll be, the velocity will be apportioned, okay, exactly proportional to that mass, and that the end result will be is that it that this balanced beam won't, the carts will move at a rate where they are always in the 2-to-1 position. That is the position where for every hunk of distance this has relevant to its mass, this one will move the exact percentage necessary to always keep the lever balanced. And so it's a really good, it's called conservation of momentum. Yeah, it's a really good example of conservation of momentum. And but it begs the question, what happens when, okay, I make this other cart heavy enough that it doesn't move. And so I guess I'll talk a little bit about that, but we'll play the video just to, you know, it's really a nice illustration.
We got a blue cart with the plunger. We're going to push this in all the way and lock that.
Yeah, it's too bad those springs are always so rickety and crappy.
We've got our green cart. We're going to get these to balance.
So he has to have them a little off center, you can understand, because of the fact that they're, you know, not the same mass. So he has to, you know, skew it to one side a little bit, but again, it works out perfectly. So a little extra 250 has to be shoved over to the other side, is essentially what it comes down to, right? The 750 needs the extra 250, so 1/4 of the car is pushed over the side of the balance to make the two sides weigh 1,000 each.
And trigger it. So you should be making a prediction. The green car is heavier by 500 grams compared to the blue car. This is about 750. This is about 1250 grams. I'm going to trigger the spring.
So if it was 2-to-1, that is, if this was 500 and this was 1,000, then we'd expect the blue car would go twice the velocity and obey essentially the law of the lever, in the sense that it would be in a position that's twice the distance of the green car.
You're just going to send the cars outward. We know there's conservation of momentum. make a prediction
So apparently we're not supposed to know that, though. So all these people are going to prove there is no conservation of momentum.
about what's going to happen. Is this side going to lean? Is this side going to lean? So think about that for a second. Here we go. 1, 2, 3.
So, like I said, they go off at exactly that. This isn't 2 to 1 because of the masses aren't 50-50. So it's more like 1/3 to 2/3 kind of difference in the velocities. But the fact is their positions on the lever are always the appropriate positions to perfectly balance. I mean, just perfectly. So the one car falls off and the other car, the blue car obviously is going faster, it falls off the edge sooner. And then you can see dramatically that the weight changes, the balance tips, and you know, it's proving the point. So, yeah, I think really good demonstration. I don't know what he does here. Oh, okay, it's just slow motion. Okay, slow motion with unnecessary sound, frankly. No, but really good experiment in the sense that we can change the weights of these cars to anything we want to, and it'll always work. So that's the neat part, theoretically. But we should never be making more energy. So I shouldn't be able to put 2 heavier carts on and get twice as much momentum, and then put lighter cars on and get, you know, 50% or 25% of the momentum. So that's the part that doesn't make any sense. So the unfortunate fact is that, yeah, we don't get to see this experiment done with, you know, 20-ounce cars and then go up to 40-ounce and then 50 and then 60 and then just see it done in all the ways that should be done to sew up any misconceptions about how it's working. All right, so there's another one I haven't seen. I have to see how that one goes. Anyway, so at least, yeah, there's now and then you can find another video that might be useful. So he has a couple of pendulum videos that are interesting also. They're not exactly on the subject, but, you know, they do show the difference between changing the mass of the pendulum or changing the length of the pendulum and that kind of stuff. Alright, so I guess I'll go back to just drawing this real quick and such. So what this makes me wonder is, okay, and I mean, you know, I have some life experience or just grammar school kind of notions of what should be expected. So the point is that you have a spring, and it always is going to, no matter what mass I put here or what mass I put here, that should have been a question mark. What it's going to do, the spring, is it's going to give 50% of the energy, okay, to each side. It's just going to divvy it up. It'll do the math and give each side half of the energy. So if this is lighter, then it'll go, if it's half as much, then it'll go twice as fast. If it's some other fraction of a weight, it'll be that fraction faster. But what happens if, okay, I put something here that doesn't move, and now I have the spring, right? This cart really does have to do what this side didn't do. So if this side doesn't move, this cart, if it was going, let's say it was going at 10 miles per hour when it was sharing with this one, half the energy, then we know it's going to have to go, if I take the same mass cart and I put it on here, and it was going 20 when both sides moved, 10 I mean, then we know it has to go 20, okay, when one side is fixed and doesn't absorb any energy, doesn't yield at all. So if it doesn't yield, it doesn't move at all, it's not going to absorb any of the energy, and it's going to actually increase the velocity. So it's like the gun argument. You could make this gun argument that if you could, you know, if you could actually mount a gun to an anvil, okay, something that just can't move, something extremely that you can't take energy away from. Like even a car doesn't really work because, yeah, you can take some of the velocity off the car. You know, it's a cushion. It's got some springiness to it in terms of its momentum. and so you would actually move it. But you need something that's just tied to the ground in such a way as that it doesn't move at all, and then it seems to me guaranteed you're going to increase the velocity of the bullet. You really don't have a choice, because it's not going to be sharing its momentum anymore, and all of the momentum isn't, if it doesn't go this way, if nothing yields here, it has to bounce back. So we're back to the argument about dropping things on an anvil, and if it's a hard anvil, we guarantee that it doesn't yield at all, that the surface doesn't dent. This thing keeps bouncing 200 times. And if it is dentable, it's 4 times, and all the energy is gone. So I mean, it really just depends on how solid the thing is you're trying to move, and if it's too solid to move and it doesn't yield at all, then you've got to increase this velocity. So anyway, so that's an experiment I want to see. And I certainly want to prove eventually that this spring can't make different momentums. It can only make a certain amount of momentum, and it always has to go somewhere. So you can't have an experiment where I put one mass objects on, okay, and then I do it the same experiment with 2s, okay, same spring, same compression, and in one case I get a total momentum going in both directions of 100, and in the other case I get 200. Somehow I increase the amount of momentum the spring can create, and I could go to 3s and get 300, 600 really, just but anyway, that doesn't happen. I mean, if that's what your results are doing, if that's what your experiment's doing, there's something wrong, because frankly the spring really can't make more momentum. Really can't. So anyway, so I don't know if there's anything else worthy of dealing with in this video. Just saying, go ahead. Okay, these people are just doing these terrible, frankly, the theory behind their experiments is junk. Okay, so the theory of making a tiny little dent, in a big blob of clay, okay, and measuring that is kind of silly. So I'd say right on its surface, that's a nonsense experiment. And the rest of it is just more complaints about the idea that you really should recognize that you have to have some kind of standard release mechanism. It is really just bullshit to be letting things go with your hands, not good enough. And so we'll see if they clean up their act or not. And if not, then again, eventually I'll have to do these experiments, which obviously physicists should be doing. I mean, it's unfortunate that this guy has a pretty good channel, lots of experiments, but none of them get to this point. And the funny thing is, right, the one experiment where he does do the Professor Lewin experiment, he doesn't show the results. It's one of those things where, what's your prediction? You do the math. What do you say happened? But he doesn't show you what happened, which is kind of hilarious. So, because maybe it didn't come out the way he wanted it to, so he just turned it into a question instead of an answer. Instead of demonstrating the phenomenon, he used it as an example of, well, you predict. But yeah, he didn't show the outcome, so we don't know what the truth is. So I probably should play that video just as an example of, well, gee, isn't that just too silly? And even in this experiment, it's just a little bit silly to use these why aren't you using this simple relationship, 2-to-1 mass? Why this weird mass relationship? So anyway, just part of internet fun, I guess. So, I don't think there's anything else. It's just, I don't think I'll go see if there's anything new from the other idiot. Alright, so it does appear that Dispar has done the coupled oscillator as I suggested, and found that instead of being impossible, it's quite possible to do it the way I suggested. So he's conceded that point. It looks really good, frankly. He's still getting his 1.4 thing, so he's all feeling quite smug and all that crap. But again, this is the free momentum experiment. So this is another case where he's creating extra momentum. So we have an experiment where you put a certain amount of momentum in and you get more momentum out of the experiment. Somebody actually said in one of the comment sections, one of the whatever cranks, why does he keep accusing us of being free momentum? Well, this is why. It's because these experiments have that as a consequence. And it's, in my opinion, okay, it's a really bold thing to say that you can destroy momentum and create momentum out of nothing with no explanation for where it comes from. It just appears. All right. So if they gave some explanation, you might be able to say, okay, it means something. But so obviously, yes, I was wrong to think a coupled oscillator was going to be a simple demonstration of the fact that you have to conserve momentum. So apparently it's not going to be a simple demonstration. But there is still, there are catches to find here. So he's fixed the fact that he didn't have the timing gates quite right. I'm not exactly confident that he still has those dimensions right because he doesn't use the same thing, but whatever. Can't be that far off, I guess. And so he's decoupled, gotten rid of all the stuff that really did connect things, but he still left it with this. He's got like a rickety little stick that he's got the pendulums tied to, and he can easily slide the pendulums. That's probably not ideal. I mean, I would say the fulcrum is critical. The fulcrum has to reflect all of the energy, and any flexing in the fulcrum, again, that's another storage device. You don't want a storage device anywhere in this system. So I'd say this might be suspect, like a bad anvil, and you're going to do the bouncing test, right? It's not going to work if you're using a bad anvil. Well, this test ain't going to work if you're using a flexible stick. So I can't see how. I mean, this is only 100 grams or something. It's not much weight, not much torque. Probably isn't bending it, but I don't know. I don't know how weak or strong the stick is. So I'm just saying it's probably better to use something more rigid. A lot more rigid. Something that can't store energy.
Now, nevertheless.
So, I mean, like I said, it's a little stick and he can slide really easily the pendulum strings. Now, that's probably not good either. So either make them so they only can be in one position, or tape them, or do something to make sure that they're not moving. Okay, that the center of the pendulum isn't moving, because of course that'll change where the fastest velocity is.
The results are still pretty much the same, between 1.44 and 1.48, which is higher than the previous one, which was 1.39 and 1.4.
Yes, well, that's you change the mass to ratio, so you're not exactly 50, 2-to-1 now. You're a little tiny bit heavier, but you put the plastic thing on the lighter mass, so it's not quite 50-50. I mean 50-100.
But still nowhere near to 2 times velocity. I can't do it. I
Okay, whatever. You can't do it. Okay, it's fine. I'm just saying that, look, when I did it on my porch, it sure looked like twice the velocity to me, but that's just the way it looked. Okay, so mine didn't look like yours, but that might not mean anything. All right, and we're still stuck with, there's a lot of experiments that sit there, you do them casually, and it does this, free momentum thing. I'm just saying you're still stuck with the theoretical implications of free momentum. And the fact that you're destroying the momentum going the opposite direction. So all of a sudden you're telling me that, look, when the system is got all the energy on one side, do you agree that all the energy is on one side or not? And obviously that's sort of the question, is maybe some of the energy stored in lifting or dropping these masses based on the tension on the pendulums. But I'm just saying, you do understand this is not a minor claim you're making, that you can create free momentum.
I can't do it. I can't make it twice as fast. So if you have any more suggestions.
Well, I can just you fiddled with you slid this thing across here, which was not great because now this isn't even centered, and maybe you should do the centering without the weight, I mean, theoretically, right? You're sitting there putting the weight on, and making your centers based on where the weight moves the paperclip moves the two objects. Well, ideally, you want the centers to be where it's going to be when the paperclip isn't affecting them. I mean, the whole point is to have the one thing moving and to have it moving when the other one isn't, so that when it moves from this way to this way, the paperclip's doing absolutely nothing. It's not putting any tension on it, theoretically. I mean, and you should initiate it by starting the velocity from inside out. So instead of pulling it out that way, pull the weight in this way, because that way you're not putting any tension on the string. You're relaxing the string. So if you pull in, you're going to relax the string. So you're not going to be adding any energy by pulling this, and then that will pull the other mass out. So you're going to take away another little factor that might be screwing something up. I mean, it's still not going to, like I said, 1.4 is a huge difference. 2 to 1.4. But anyway, the point is the velocity clearly isn't representing it being twice the energy. Now, maybe the arc is, so I'll measure the arcs. At least the video is good enough quality to do some frame rate stuff and other things. So, yeah, we'll see what happens.
But, yeah, it's becoming kind of hopeless no matter what I do, no matter.
That's how he keeps saying it. No matter what I do, whatever, blah, 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 blah. Like he's done everything that could possibly be done on Earth. I mean, there's so many things I've pointed out that ideally this pendulum should be, 6 feet long. I mean, lots of things should be different if you want to really measure it, So don't be saying you've done everything you can do. Pathetic.
What I changed to the setup.
And again, what you haven't done is explain how it's possible to make free momentum without using any fuel for your free momentum.
The results revolve around the same results. Between 1.4 and 1.5. Well, 1.48 at best. So, I guess you'll have to do the experiment, because I can't make it happen.
Yeah, fine. I did do the experiment, actually. But yes, I'll have to do it where I can, get a good enough, some measuring metric, okay, that I can use, because I won't be using timing gates. But we'll see. I'm just saying, you're making a bold claim. This is the experiment you're showing. Okay, fine. You're not going to show me taking from 16 times the fuel to go 4 times as fast. You're not going to show something going 4 times as fast doing 16 times the damage. You're not going to show me car crashes. You're not going to show me this, that, or the other thing, right? All this other stuff that would be pretty decisive. And so this is what you're going to show me. And I'm going to say, oh, gee, free momentum. I don't think so. I really don't think it works that way. So good luck with that theory. All right, so that's all I got to say to that. But yes, it's an improvement. I'm glad he was willing to improve the experiment. But again, he was so emphatic that it can't be done. It can't be done. Yeah, and it could be, because I understood the theory and you don't. I mean, I'm still going to make the basic argument. There's only 2 choices here. You have energy in something moving. All right, it's going to go with velocity. Now the trick is that obviously you're using gravity to create the force, the motion. We're not, using some other mechanism to push something with a velocity. So it's accelerating through the whole path that it's falling in the pendulum. The pendulum's accelerating, and there's a key point right here at the base that's going to be. This is where it goes the fastest. Now, that's only true, though, as long as the pendulum itself isn't moving. Because then the point is going to be a different point. All right. So there are some things to think of. But there's only 2 places the energy can be. It's either in the thing's velocity, or it's in the fact that you lifted it. There's only 2 places energy can be. Lifting, that takes energy that you can take back later by dropping. Or the energy has to be in the velocity. So if I have a slow velocity, I can assume I've raised something higher. And if I have a full velocity, then I can say, well, I'm at the lowest possible point. I mean, that's sort of, it's the way pendulums work, is this the solid truth. If I raise a pendulum as it's swinging, I will decrease its velocity, because the raising was storing part of the energy that the pendulum had has now been lost to gaining the extra height. It had to use its velocity to go higher. Okay, it can't use anything else but its velocity to go higher. Alright, so it has to be in those two places. And so you have two objects that are either in a position up and down, or they're moving this way. And all the energy, in my opinion, has to be in those four places. In this motion of the two objects, or in the up and down of the two objects. And it can't be anywhere else. Now you tell me it can be somewhere else. Go ahead and tell me that. Explain it to me. Alright. So anyway, we'll see till next time and such and so forth. I'll attempt some video editing and see what I can make out of his video. Unfortunately, the best I can do is download it in 720p, but that should be good enough. So we'll see. Let's see. So, well, anyways, you have to have timing gates to test this properly. Now, there's lots of ways to test something. You can use sound. I mean, that does actually work. I can just plug a wire into my mic jack, and if I have little tiny wires that have just hit each other when you hit them, and they make a sound, that's all you need. And you can measure it by time. No problem. So I can make my own version of that, but whatever. There's other ways to do it, frankly, and I'll find one of those other ways. But anyway, till the next time and such. But frankly, the experiment, he's done it fairly well, and what's really missing is any kind of theory. Explain what's happening and why it's happening. I mean, explain where the free momentum is coming from. Alright. So, till the next time and such and so forth and whatnot.